Okay, so if you look at this next chapter, it's about the structure of atoms. And I'm going to zoom in a little bit so that we don't have all this space down here. So we're looking at the structure of atoms. And going through here kind of quickly, section by section, the very first section is called electromagnetic radiation. And the reason it's called electromagnetic radiation is because there's an electrical component to it, and there's a magnetic component to it. So it turns out that electricity and magnetism are interwoven. When you have one, you have the other. In this particular section, they talk about the wave model. And they draw a little picture in the book, which I can't draw very well, so I'm just going to show it to you, okay? So this is the picture of electromagnetic radiation, and you can see that we have two components, and they're perpendicular to one another like that. So one component, in this case, the blue component, is going to be the electrical component, and the red component here is the magnetic component. And when they say the direction of propagation, you got to think the wave is coming towards you or it's going somewhere. And it's really kind of going somewhere like a snake goes somewhere. So it's a wave. So we've got the wave model, and I'll just draw one component. So here's the wave, and these are kind of like waves at the seashore where they're moving towards the shore. So here, if we have the ocean here, and then where the water meets the ground, we have the shore. These waves are moving towards the shore. So that's the idea of the wave model, is that you have an electrical component and a magnetic component, both oscillating and moving forward. Now, this part here, from the middle of the wave to the top of a wave, is called the amplitude. And this also here is the amplitude going down here. So that would be negative amplitude. And they use the letter A for amplitude. And for the amplitude, that might be equivalent to something that we call intensity. So what do I mean by intensity? Well, the easiest way to think about intensity is if you had one flashlight, the beam would be intense. If you had two flashlights of the same type, the beam would be twice as intense. So that's intensity. Okay, there's this distance here. This distance here is called wavelength. And the symbol for wavelength is this letter here. It's called lambda. And the wavelength is often measured from top to top, and sometimes it's measured from bottom to bottom, or it can be measured from, say, here to here. So here we have the downsloping of a wave, and then the downsloping of a wave. The idea is that the wavelength is the distance between any two like points on the wave. So you can measure the wavelength a number of different places, but most commonly it's easiest to say, well, crest to crest or peak to peak. Now, the other thing about the waves we have is something called frequency. And for frequency, we use the letter nu. This is a Greek letter. On a lot of physics textbooks, they'll use the letter F for frequency. And this is equal to waves per second. And normally we don't say waves per second, we just say per second. So the official units of frequency are per second. And we also say that that's a hertz. So 1 per second is the same as 1 hertz. Uh, and here, of course, we have wavelength. And wavelength is measured in meters. Okay, so that's electromagnetic radiation. And then there is the speed of the electromagnetic radiation. So speed is different than how many waves are coming per second. It's how fast this whole thing is moving. And the speed is what we call the speed of light. And it's 2.998 times 10 to the 8th meters per second. And they say that this is, of course, in a vacuum, which is where light mostly travels through. It travels through a vacuum. Most light does not travel through air. You know, if you think about light coming from the sun to the earth, the amount of air that the light passes through compared to the amount of space it passes through, um, it's practically passing through no space whatsoever. So here, when we talk about the speed of light, it doesn't seem relevant to us because we live in air, but it really is relevant when we talk about how fast it travels. And it doesn't travel that much slower in air. So this is the very first section about electromagnetic radiation. And there are how many equations? One equation that they give you that you should memorize. But before I give you that, well, I'll go ahead and give you that equation. So this is still electromagnetic radiation. And true to form, I don't like writing a lot. So instead of writing electromagnetic, I'm writing EM for electromagnetic. The equation you want to remember is this. The speed of light is equal to the wavelength times the frequency. That plays an important role for the rest of the chapter. So you want to know this equation. Okay. The other thing that you want to know from this particular section are the different types of light that we know about. So there's something called gamma rays. And the symbol for gamma is this guy here. There are X-rays. There's ultraviolet. And the symbol for ultraviolet is UV. And then there's visible. And the symbol for visible is VIS. And then there's infrared, which is IR. And then there's microwaves. And then there's radio waves. And the book actually separates radio waves into short radio waves, long radio waves, and well, I'm not going to bother doing that. Now, what you want to know about this is that if I draw energy here, the arrow going to the left means at the left, this is high energy, and at the right, that's low energy. The arrow always points to where there's more of it. So more energy in gamma rays than radio waves if you look at them comparatively. Now, on the other hand, if we look at another thing, if we look at wavelength, these are short wavelength and radio waves are long wavelength. So energy and wavelength are opposed to one another. Smaller energy will mean longer wavelength and larger energy will mean smaller wavelength. And you should know the visible spectrum goes from 400 nanometers, low wavelength or short wavelength, to 700 nanometers, which is a long wavelength. And the colors of the spectrum are VIB, GYOR. V stands for violet, I for indigo, B for blue, G for green, Y for yellow, O for orange, and red, R for red. The difference between indigo and blue is like indigo is a really, really, really deep blue, and blue is more like a sky blue. So indigo and blue are, to me, different shades of blue, but apparently they're different colors. I'm just not that good at that kind of stuff. Okay, so do you understand this first section? The important parts of it, the things that you might want to know. So you should be able to use that equation, C equals lambda frequency, lambda nu. So I'm just going to make up an equation. Calculate the frequency of, let's say, blue light with wavelength equal to 486 nanometers. So that's the problem we're going to do. So we know that C is equal to lambda nu, and we want the frequency. So frequency is equal to C over lambda, and we plug in these values. So C is 2.998 times 10 to the 8th meters per second. And the wavelength is 486 nanometers. But now look at what I'm doing here. Do you see what I did there? So rather than leave the nano in, I just changed it to 10 to the minus 9, which is totally legal because that's what nano really means. So now meters cancel, but the second doesn't. So our answer is going to be over second. And let's see, where's my calculator? I'm having trouble finding my calculator. So guess what, An? You got to do the calculation and tell us what the answer is.
I
So
think the answer is on, let's see, 368, right? 1.97, 1.98 times 10 to the power of negative.
No. Let me show you my estimate, okay? This is how I'm gonna estimate it. Did you see how I made 10 to the 8, 10 to the 3rd times 10 to the 5? So 10 to the 3rd times 10 to the 5 is 10 to the 8th. So do you see how 10 to the 3rd times 2.998 is 2,998? Are you okay with that? Oh, you disappeared.
Oops.
And you're back.
Finally. Yeah.
Okay, I'm showing you my estimate. You told me 10 to the minus something, but that's not correct.
Oh, that's not.
No. So here, do you see 10 to the 8th is the same as 10 to the 3rd times 10 to the 5?
Yeah.
And then 10 to the 3rd times 2.998 is 2,998.
Oh, yeah, I see what I do wrong.
And then this goes into this about 6 times. And so we get 6 times 10 to the 5 and then times 10 to the plus 9. Because when this goes into the numerator, it becomes positive. So the answer should be around 6 times 10 to the 14 per second.
Mm-hmm.
So what'd you get? Are you still getting,
let me try to put it in the
are you still getting like
calculator.
10 to the minus 4 or something like that?
Let me see. Yeah, I got 6. Yeah, they're pretty close to you.
Okay, 10 to the minus 4 though, right?
No, it's positive 4 actually. It's I got 6.17 times 10 to the 14.
Okay. And that's per second. So there's your
Yeah.
answer.
Yeah, I think I put it. I messed up on the
Okay.
calculation.
When you messed up, did you use the caret thing?
No, my calculator we can put it on power like this, but I messed up on the division,
Okay.
so I put this multiplication instead of it.
Okay, so that's pretty much the first section. The next section is called quantization. And it talks about Planck, Einstein, energy and photons. And I don't want to go into all the lecture stuff, but I'll tell you that Planck came up with an equation that says E is equal to h nu. And h is called Planck's constant. Which is 6.626 times 10 to the minus 34 joule seconds. And notice I said joule seconds, not joules per second. So when I say joule seconds, the second stays in the numerator. And this is energy. And the units will be joules. And of course, nu is frequency. And the units are 1/second. So if you have h being joules times seconds times frequency 1/second, you'll end up getting joules for energy. So this is Planck's equation. And this is still treating light as a wave. But then Einstein came along and he said, you know, let's have a different model of light. So Einstein came up with another model of light. His model was the photon model. So instead of having a wave, a photon is a packet of energy. And it has no mass. So instead of the wave form of energy, you now have these little photons of energy. Okay. Now here it's kind of a mistake for me to draw these things because then it looks like it's a ball, right? And it's not. It's just a packet of energy. So no mass, just pure energy flying through the air. And he developed this idea from the behavior of something called photocells. And I'll let you read about that in your book. But the rub of it is that for Einstein's model, we still get to use E, but this is the energy of one photon is h nu. So when we use this equation, we're actually calculating the energy of one photon of a particular wavelength. Okay, so that's the big equation there. And let's see. Again, I'll let you read about the photoelectric effect yourself, but you can see that this equation ties in with the previous equation. So let's look at quantization. And the wave model. of light. So with the wave model of light, we have C equals lambda nu. And with the quantization, we have E equals H nu. Now this, if we rearrange it, becomes nu is equal to C over lambda. So we can take this and substitute it in right there, and we get E equals HC over lambda. And this is a pretty important equation along with these two equations, because sometimes we don't have the frequency, but we do have the wavelength, and we can calculate the energy using the wavelength directly. We don't need the frequency because H is always the same, it's a constant, and C is always the same, it's a constant. So a great deal is made out of this. So you should know this equation. So here we could calculate the energy of a green photon with wavelength equal to 486 nanometers. So this is that same green wavelength we used before. Here, the energy of the photon would be equal to 6.626 times 10 to the minus 34 joule seconds times 2.998 times 10 to the 8th meters per second. And then all divided by 486. And what am I going to do here? What's my trick? Do you remember?
It's 10 times to the negative 99.
Yeah, 10 to the minus 9 meters. That way I don't need to deal with the nano.
Yeah.
Meters cancel, seconds cancel, and we get joules. So go ahead and use your calculator and tell me what answer you get.
Yeah. Ooh.
Did you get an answer yet?
I got 4.09 times 10 to the power of negative 19.
Okay, 1.09 times 10 to the minus 19 joules. That sounds about right.
4 point, not 1.
Oh, 4.
Yeah.
4.09 or 4.109?
4.09.
Okay.
Yeah.
So there you go. Another thing that the book has you do is something like this. Calculate the wavelength if 1 mole of photons has the energy equal to, let me think about this, 22.4 times 10 to the five joules. Now, one of the things that if they give you this, the energy per mole, so oftentimes they say this, the energy is 2.4 times 10 to the 5 joules per mole. We can't use this equation because this is the energy of 1 photon.
Oh.
Not 1 mole of photons. So how do we do this problem if we're given the energy for a whole mole of photons? Well, you take this 2.4 times 10 to the 5 joules per mole, and you multiply by 1 mole is 6.626 0.022 times 10 to the 23rd. So what do you get when you divide these two?
I will get Joule. It's kind
You will
of,
get joules,
yeah.
but what do you get numerically?
Is that like one proton?
Yo,
Is that
this is
right?
going to be, yeah, for photon. So this is photons.
Yeah. Joule over proton. Okay.
So I can't find my calculator, so you have to do the
Yeah.
calculations. I have no
Wait a
idea
sec.
what I did with it. It's awesome space.
I think I got 3.99 times 10 to the power of -19.
What? Oh, 3.99. Okay, that's fine.
Yeah.
So you get 4.0
Yep. Technically,
times
4.0
10 to the
times 19. -19.
negative 19.
Yeah.
Okay, so now we can use this equation. So lambda is equal to hc over energy. And now we can use the equation. So 6.626 times 10 to the minus 34 joule seconds. 2.998 times 10 to the 8th meters per second. And then 4.0 times 10 to the minus 19 joules. And joules cancel, seconds cancel, and we'll be left with meters. So go ahead and do this work and tell me what answer you get.
I think I got 5.0 times 10 to the -7 power of
Okay.
-7.
So can we see this?
Yeah.
Is that visible light?
I think so.
Well, how would you know? This is meters. We know that we can see from 400 nanometers to 700 nanometers, right?
Oh.
Does
Okay.
that fit in there?
So we have convert to nanometers. So we
Yeah,
can
that's the
compare.
best way to do it. And to do that, you multiply by 1 nanometer over 1 times 10 to the minus 9 meters.
9.
And what we end up getting here is 5.0 times 10 squared nanometers, which is about 500 nanometers. So is 500 nanometers in here?
500. Yep.
Yep. So we can see it. It's visible light.
Oh, I have. Can I ask you a question real quick?
Yeah.
Is that the on the calculation the 6.26 something? Is that for the
That's for
constant?
Planck's constant H.
Planck's constant. They always like that, right?
Yeah. Well, that's why they call it a constant. It's because H is always that number.
All right. So I think I had to
C is a
memorize
constant.
it.
It's always that number. So yeah, it's always like that.
Yep.
And that's precisely what constant means. Always the same.
Yeah.
Okay. The next section is called atomic line spectra and Niels Bohr. Okay, so what I'm going to do here is I'm going to try and pull something up off the internet to show you. It'll take me just a moment here. Okay, great. I found an image that I'm going to show you. It's taking a little bit of time to come up. Oh, because it's a video? Damn it, I don't want a video. Okay, here's a different one. This will be fine. Whoops. Okay, so let's take a look here. I'm going to change my share. And you're going to be looking at my computer screen. So can you see the image with, you can just give me a thumbs up. Can you see the image with 2 light bulbs and a hot gas? Okay, good. Let's look at the top image with the light bulb going through a prism and then going to your eye. So the eye is really a detector, okay? If you had a light bulb go through a prism, you would end up seeing, so instead of the eye, let's pretend that the eye is a screen that the light is shining onto. So it's kind of like a movie screen. But instead of a movie, we're seeing what's coming off of the light bulb. So if we were to take the light bulb and shine it through a prism and then project that onto a movie screen, we would see a continuous spectrum of all colors. So you can see here, they have this arranged not as Viv Gyur, but it's arranged as Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet, Roy G. Biv. So they kind of have it backwards from what we were talking about before, but that's fine. That's no big deal. Now that's called a continuous spectrum. You see continuous spectrums from a lot of light bulbs that have filaments in them. You see a continuous spectrum from the sun. If you were to take a branding iron like you use on a cow to put a brand on it, and if you were to take that branding iron, put it in a fire and make it white hot, that white hot light would be a continuous spectrum also. So white light generally gives you a continuous spectrum. Now, I'm going to pull up another image and I'm going to look up the spectrum of mercury. Okay, so I'm going to look at images here, and I'm going to get a nice image of a mercury lamp. Okay, so here's one. So can you see the image here of the graph in the middle of a mercury lamp?
Yeah.
So let me just show you what you're seeing there. Do you see the wavelength at the bottom goes from like 300 nanometers to about 800 nanometers?
Yeah.
So we're going to focus just on the stuff between 400 and 600 or 700, because that's what we can see. And you see how the background there is kind of a Viv Gyur, violet, indigo, blue, and all that stuff?
Yeah, yeah. Like
So this is
rainbow.
not a continuous spectrum. It's called a line spectrum. So we would be able to see the 406 nanometer light, the 436 nanometer light, the 546, and the 579, as well as that little peak at 500. That's what we would be able to see, but our eyes aren't able to distinguish those things. We can't tell them apart from one another. So what happens when all of that light hits our eye together at the same time? And the answer is, since it's a little bit of every color, it looks white to us. This is how fluorescent lights work. Fluorescent lights actually have mercury in them. And when you excite the mercury atoms, they give off different lines, not a continuous spectrum, but different lines. And so what is the origin of these lines? Why is it not continuous? That's, was a great mystery of the time. So let's go back to that other thing that I was looking at. So here, if we look at the second image, the middle image where it says a hot gas, this is what happens when you heat up a hot gas. You send the light through a prism, but instead of getting a continuous spectrum, you get lines. Now notice where the lines are, and in between the lines, it's black. Why is it black? And the answer is, it's black because there's no light there. There's no light of that wavelength. So you only see lines of the wavelengths where we can see the colors. So that's kind of interesting what's going on there. That's called an emission spectrum because the gas is emitting light. And when you project it onto a screen, that's what you see. Now, the last figure is really telling. It is a light bulb that you shine through the gas, but instead of having a hot gas that glows, it's just a cold gas. So coming out of the light bulb, we know we have a full continuous spectrum coming out of the light bulb, all of the colors. But when you shine it through the cold gas and then through the prism, you don't get a full spectrum. You get most of it, but there are black lines in there. Those black lines are at the same places where you see colored lines in the emission spectrum. So this bottom one is called an absorption spectrum because some of the continuous spectrum is being absorbed and it doesn't get through. And when it doesn't get through, it looks like a black line. So you kind of understand the differences between the three images on?
Yeah. So the cold gas, they absorb the light from the light bulb.
That's the idea. The cold gas is absorbing the light.
Is that like some kind of relate with the heat when they absorb it and they
Well,
heat it up?
that was the great mystery. Why does it absorb light? Number one. And why does it absorb the same wavelength that it emits? Doesn't that seem weird?
Probably
Yeah, I think
like
kind of
really
relate a
weird
little bit.
sort of.
They are related.
Because light sometimes they have the heat on it, right? Energy.
Right.
Which is
So
when they absorb it, they turn into the hot gas.
yeah, so let me
That's what
show
they
you what's going on here. So when you have this hot gas,
Oh, I think you
oh, I got to share my screen. Thank you.
Yeah, bench press and stuff.
Okay, so
Upper body.
here for the hot gas, light goes through the prism, and then you get a line spectrum. So maybe you get a green line, maybe you get a red line, and maybe you get a blue line, right? So here's what they say is happening right here. If you have an atom, and this is your nucleus, so we're going to make this a hydrogen atom. The electron on the atom can be in different orbits. So with a hydrogen atom, you have one electron and one proton. So the nucleus is a proton, and the electron can either be in the first orbit, the second orbit, the third orbit, or the fourth orbit, all the way up to 7. Are you with me there? So this is a Bohr's model of the atom. Bohr's model is that you have a nucleus and electrons orbit around the nucleus, like planets orbit around the sun.
Yeah.
Okay. Now, let me ask you something. What is the relationship between the nucleus and an electron? Is it a repulsive force or is it an attractive force?
What's it? They go together is re-
We call that
repulse?
attractive.
attract. Yeah.
Okay. So when
Yeah.
they like each other, they're attractive, right?
Yep.
So if I take this electron and move it to the second level, am I
Mhm.
going to have to put energy in, or is that going to give off energy? In other words, does it absorb energy or does it emit energy? If I want to go from here to here.
I think they have to absorb more
Very
energy.
good. That's going to absorb energy.
Mm.
Now, what if I have an electron here at the second level and it goes back down to the first? What's that going to do? Absorb energy or emit it?
Definitely emit it.
Emit it. Okay. So here, that's going to emit energy. What does the energy look like? The energy looks like a photon.
I didn't even do the reading.
Mhm.
So
And here, what gets absorbed here is a photon. Photon absorbed, photon emitted. So this is what's happening with the hot gas. With the hot gas, you're taking electrons and
shit,
you're
the quiz
making the
might be on that. Oh my
electrons
God.
go to a higher level. But when you put energy into the hot gas,
Oh,
the electrons
shit,
don't
yeah.
stay at that higher level. They drop back down. And when they drop back down, they emit light of a
Questions from
particular
the-
wavelength, depending on this distance here.
I mean, yeah, we are last pod.
And so that's how you get a line here. This might be like an electron going from the third level to the second level. And maybe this one is an electron going from the fourth level to the second level. And this could be an electron going from the fifth level to the second level. So you get all of these emissions because electrons are moving from one level to another. So that explains this right here, the emission spectrum. What explains the absorption spectrum? Well, the absorption spectrum is these particular wavelengths are absorbed when you excite the electrons, when you move them up.
like the
So
light, right?
yeah, so that's how they're connected. In one
Okay.
case, these guys absorb the wavelength and they're missing.
Mhm.
And in the other case, these guys emit it and they
You guys
show
do
up,
your
but they're
math
the only
homework?
ones that show up.
Oh, okay.
So that's Bohr's model of the atom.
Mm.
Now let me show you the important equation out of here is we have energy of the nth level is negative RHC over n squared, where n is equal to 1, 2, 3, 4, basically up to 7. H is 6.626 times 10 to the minus 34 joule seconds. C is 2.998 times 10 to the 8th meters per second. And R is something called Rydberg's constant, which is 1.0974 times 10 to the 7th per meter. Now, the nice thing about this is a constant, this is a constant, and this is a constant. So you can write that the energy of the nth level is negative 2.177 something, I can't remember what, 8, I think, times 10 to the minus 18 joules over n squared. So that's the energy of an electron in a particular orbit. So the energy of the electron in the first orbit is negative 2.1778 times 10 to the minus 18 joules. Let me check this number and make sure I got it right.
Good job, guys.
We'll just assume I'm right. Now, the energy of an electron in the second orbit is going to be this number divided by 2 squared. So what's this number divided by 2 squared? It's something like negative 0.545 times 10 to the minus 18 joules, if I remember right. So based on this, what would be the energy of the third orbit?
Oh, so square. And wait, you want me to calculate it?
Yeah, because I can't find my calculator. You're the man.
Okay. Wait, so we use that and divided by 3 power 2? Is that
That's
correct?
right. 3 to the power of 2.
I don't know if they do right or not, but the answer look kind of different.
Tell me what you got.
3.4197 times 10 to the power of 19.
Okay. That's fine. Let
Oh,
me think
it's
about
2.4, not 3.
2 point. Yeah, I was going to say 3.4 is not right. This number you gave me is the same as 0.242 times 10 to the minus 18 joules.
Oh, never mind. I got it.
Your calculator is fine.
Yeah.
So the real question is, why am I writing this way and not in scientific notation? And the answer is so I can compare these three numbers.
Yeah.
Which of these three is the biggest?
Oh, definitely
First, right?
Yeah.
Isn't 2 bigger than 0.2?
Yeah.
Ignore the
Maybe-
negative sign. We don't care about
Okay.
the negative sign.
All right.
This is not a trick question.
Okay, so that's like
So 2 is bigger than 5 is bigger than 0.2, right?
yeah. Definitely.
So a kind of interesting thing is, where do these energies come from and how does this equation work? Well, and this is the last thing I'm going to leave you with today. You can actually count the change in energy of an electron. The change of energy in an electron is equal to the energy final minus the energy initial, which is negative RHC over N final minus negative RHC over N initial, because energy is negative RHC over N squared. So the final energy is negative RHC over N final. The initial energy is negative RHC over N initial, and we can clean this up. So do you see what I did there?
Yep.
Oh,
And I'm going to clean it up some more by putting 2.18 times 10 to the minus 18 joules So rather than have that, I'm just going to put a number there.
Yeah.
So here's my nucleus. Here's my first orbit. Here's my second orbit. Here's my third orbit. Are you with me?
Yeah.
So here, this is an electron in the infinitieth orbit. So what do I mean when it's in the infinity orbit? Well, the infinitieth orbit is so far away from the nucleus that it's not part of the atom. Are you with me?
Yeah.
So this electron is not part of this atom. So when the electron drops down to here and ends up in the first orbit, let's calculate the change in energy, okay?
Mm-hmm.
So the change in energy is going to be negative 2.18 times 10 to the minus 18 joules times 1 over 1 squared minus 1 over infinity squared. So what's 1 over 1 squared?
1.
Good. Didn't need your calculator, did you?
No.
What's 1 over infinity squared?
1 over infinity square.
Yeah. So 1 divided by a really, really, really big number. What
Yeah.
is it?
It's pretty small, right? Really
What's that?
Small. It's really small.
Really
number,
small. How small?
Like really, really.
Really, really small, like close to what? Close to 1?
uh, is that infinity? Okay. I
No.
mean, like it's
Well, let's take a
zero,
look.
0, 0.
Let's say 1 over 1 is 1, right?
Yeah.
1 over 10 is 0.1, right?
Oh, it's close to 0.
It's close to 0. That's what I wanted
my
you to get
brain.
to. Because eventually, if I put 1 over a million,
Yeah.
we would have 0.000001.
Yeah.
And you see, we're getting really close to 0, aren't we?
Yeah, but not.
So
Zero.
what's 1 over infinity squared?
Is really close to 0.
Really close to 0. So what's 1 minus 0? It's not a trick question.
Yeah. 1.
1. What's 1 times this number?
Um.
That
Maybe-
number,
Yeah, that number.
right? Now, one thing I need to do though is
Is that just pretty close to the RAC?
yeah.
Or HNC? When the
Yeah,
H
so
is
here
used?
we get this one, which is the number we calculated way back here. Do you remember this?
Yeah.
It's the same
Mhm.
number. So this number is the amount of energy that is given off when the electron ends up in the first orbit.
Mhm.
So now, so this is the very last thing. I
Yeah.
want you to calculate the change in energy, which is negative 2.18 times 10 to the negative 18 joules times 1 over n final squared, 1 over n initial squared. And I want you to calculate it for this situation. Your electron starts here and you remove it all the way. What's the energy going to be?
Oh, we move to the infinitive.
What's that?
Let's see. We move to the infinitive.
That's
the
right.
final?
That's the final.
Okay. Wait. So that will be the positive. The answer would be pretty close to the 2.18. So
So-
it would be positive.
Okay, it would be positive.
Yeah.
So what this tells us is that's how much energy we have to put in,
Absorb. Yeah.
absorb to remove the electron.
Yeah.
So this kind of explains to us why the electrons have negative energies. It's because it's the energy they've given off to become part of the atom.
Okay. Yeah.
All right, that's it.
Yeah.
That's enough. You're probably drained from the exam, huh?
I know.
I'm trying to get the exams graded today, so people who are borderline, if they want to drop, they can drop. Today's the last day to drop.
Oh.
I'm not suggesting that you drop on.
No, I mean, like, I didn't
Yeah, if you
realize
take a
that
look,
today's the
I've
day.
also been grading some assignments, and the older assignments I'm grading very leniently.
Yeah.
So I apply the rubric to it. And after I apply the rubric, I add 1 point, and that's the score I record.
Oh, okay.
And the old rubric is pretty easy. I'm not being that hard on it. Like with the lab notebook, when it says discussion has to be thoughtful, I just give
Oh.
it a 2. I'm not reading
Yeah,
it very carefully.
I'm not really good at writing the discussion.
Well, you need to get better because I'm going to be grading
I
those
know.
harder, starting with that quantitative analysis lab.
Oh, all right.
Okay.
Yeah.
All right. So hopefully I'll have a whole bunch of stuff graded for you guys to look at later today. And then we move through the rest of the semester. You'll notice I've already posted the lab
Mm-hmm.
for yesterday. That's going to be due Wednesday. I think it's Wednesday. Your quiz is, I think your quiz I'm going to make on Thursday for this section. This section goes by pretty quickly.
Mm-hmm. Pretty short.
And then the next section is also going to be like 1 week.
Oh, next section?
Yeah, the section after this one. The section after this one is atomic atoms and periodic trends or periodic properties.
Oh, okay.
Structure of atoms
Yeah.
and periodic trends. That one is pretty quick also. And then chapter 8 is starting to talk about Lewis structures and Lewis structures and valence
electron.
Vesper, I should say.
Oh, okay.
Yeah, and I'm sure that's going to be review for you from your previous chem class. They always talk about Lewis structures and Vesper.
Oh, yeah. It's kind of by word in high school chemistry.
Yeah, so we'll be doing that. The assumption is you've had it before, so we go through it pretty quickly. So the next exam is probably going to be about 3 weeks away.
Oh, okay. Yeah.
Yep. All right. Thanks for tuning in.
Yep. Thank you.
Say
a
goodbye
good
to
day.
everybody.
Yep. Bye. Bye, everyone.
All right. We'll catch you Monday.
Yeah. See you Monday.
All right. Bye-bye.
Oh my God.